But I don't know if I want to take that next semester or like.
Take it next semester and get it over. In the next class from this one.
Well, you guys ready? Alrighty, well, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for the break we just had. And just pray that you just guide our steps today, help us to glorify you what we do, and that we just all understand how to graph rational functions after today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's get to it. These rational functions aren't going to graph themselves. Well, I mean, I guess they might. No, we'd have to be really lucky for that to happen. Like really lucky. So, short of a miracle. Let's talk about graphing rational functions. Now, so rather than give you some sort of grand, glorious algorithm, I will proceed by examples. Let me start with example 1. Let us suppose we have f of x is equal to, I don't know, x to the, I'll get it eventually here, guys. X to the 4th minus 4 divided by, I don't know, x squared minus 2. How would you graph this? Well, first thing I would do would be like long division. All right. So we've got x to the 4th minus 4, and man, this thing really moves. Anyway, sorry, I'll stop. So I have an x squared here. Multiply x to the 4th minus 2x squared. Subtract. We get 2x squared minus 4. So I do plus 2. I get 2x squared minus 4. Oh, drat. I should have known that was going to happen. Okay, fine. So this is what? Hey. What goes on here? This is x squared plus 2 times x squared minus 2 divided by x squared minus 2. Do I really need to do long division here? Not really. What do I have? X squared plus 2. How do you graph x squared plus 2? Use Desmos. Ooh. You hurt me with that. Let's see here. I mean, it's x squared plus 2. Come on. I mean, come on, man. Make a presidential request. Let's see here. So it's the y equals x squared graph shifted up 2, right? We know this. It looks like this. All right, this is 2. Now, that's a lie. This is kind of a weird starting point, but so here, this is an interesting example. This is actually a reasonable test question. Anyway, I won't explain to you guys. It's just funny. This example's funny. There's two things called holes in the graph here. See, because look, the formula that you're given, what's the domain of f? No. would be x such that x squared minus 2 is not equal to 0, right? When can x squared minus 2 be 0? This has got problems when x is what? Plus or minus the square root of 2. Those points are not in the domain, right? When is this simplification legit? That's legitimate for x not equal to plus or minus the square root of 2. Now, plus or minus the square root of 2, the function's just not defined. However, it has holes in the graph, and I can tell you where they are. They're like, you know, here-ish, there-ish, something like that. What are those holes in the graph? Well, they're square root of 2, and then this right here is what we would call the reduced function. The reduced function. So the reduced function is when you cancel out the things that give you a hole in the graph. Man, this is such a weird place to start today. My apologies, guys. Like, this was supposed to work out different, and my mind didn't work. Oh well. It's not a wrong example. It's just not. It's just weird. So the square root of 2 squared plus 2 is what? It's 4. And this hole in the graph over here is also at 4. I can see that from looking at the reduced function. If I try to plug in plus or minus root 2 into the original formula, that doesn't work. I have 0 over 0, which is just undefined, okay? So that's why there are holes in the graph. Any questions? Sorry, I didn't mean to start this lecture with a hole in the graph example. It just happened to me. So my apologies. Let me try something else here. Example 2, if I can. How about we have f of x equals to 3x squared over x minus 1. So let's do the long division. How do we go? We've got 3x squared. We've got an x minus 1. So that gives us a 3x. We got 3x squared minus 3x. Take the difference. You get 3x. Oh, okay, so plus 3. And then I get 3x minus 3. I subtract. I get 3 for my remainder. Let me collect the spoils of war here. So what we have is 3x plus 3. Man, it's all 3's. Plus 3 over x minus. It's just all 3's. I didn't plan this. Sometimes I think God has a sense of humor. I deserve it. All right, let's see here. So there it is. All 3's. It's too bad I'm not like playing slots or something. Don't worry, I would donate the money to the church. That would make it okay. Let's see here. Also, point of order, if you know you can win at gambling, it's not gambling. But anyway, so what do we got? This I can graph, what I just wrote in red. What does it do? It behaves like y equals 3x plus 3 for large values of x, right? So like think about this. This formula right here is essentially y is equal to 3x plus 3 for x going to plus or minus infinity. Because if x goes to plus or minus infinity, the 3 over x minus 1 term drops to nothing. It's nothing. On the other hand, if x is close to 1, that 3 over x minus 1 term is everything. It completely dominates the story close to 1. So this has what's called the vertical asymptote at 1. And let's see here. Y equals 3x plus 3 is what? That's, you know, it's something like this. I'm not going to do it quite to scale, but it's something like this, okay? So y equals 3x plus 3 is actually what's called a slant asymptote for the graph here. I'm going to graph this one in red because I already used blue and green. All right, so what the graph looks like is, well, it goes through 0 here. How do I know that? Well, if I plug 0 in, I get 0 over minus 1. So it's got a x-intercept of 0. And apparently it must look something like this. So it goes big like there, and if I was to, let me extend this up a bit, if you'll just forgive me for writing through my writing. So what this thing would look like, something monstrous like this, and then it does some kind of bendy thing back to like that. So the rules are the graph has to blow up to infinity or down to minus infinity at vertical asymptotes where you've got division by 0. And then also the graph has to get sucked into the asymptote of the graph when x goes to plus or minus infinity. For this one, the asymptote is actually the green line, y equals 3x plus 3, right? For this one, it's kind of stupid. We were just graphing the asymptote, essentially. The asymptote is the parabola in this context, actually. One more of these, and I'll have it out of my system. Example 3, if you had something like, oh, I don't know, f of x equals to, x to the 4th plus 1 over x minus 1 squared, what that would look like is a graph of y equals x to the 4th, all right, which would be something like this, right? There's your y equals x to the 4th. But you've got a vertical asymptote at 1, all right? So you're going to do some kind of like, basically you're going to kind of follow the x to the 4th graph away from it. And then once you get close to it, you're going to blow up like that. And then down here, we're going to blow back up like that. And then we're going to go back to the graph like that again. Sorry, my color coding is all out of whack here. I promise I will be more systematic with my color coding the rest of the lecture. This has a quartic asymptote. All right, this is the point where I admit things. There was a time when I actually tested on this, when I would actually make you guys graph slant asymptotes. And I would try to see if you're right or wrong and stuff like that. That time is gone. On the other hand, you might say, well, wait a minute. So if you're not going to test on slant asymptotes, then you're not going to test on quartic asymptotes, are you? No, I would not do that. But this one here actually is making me recalculate things. Like this, example 1 actually would be a reasonable thing to graph. That is not outside the bounds of, I think, something you should be able to do. This, trying to draw like a quartic asymptote or a slant asymptote, that's just a little bit past where we want to actually do in this course. But what I wanted to talk to you about is simply this, is if we're going to graph y equals to, if we're going to graph y equals to p of x over q of x, right? Then the graph of that is, if the degree of p of x is larger than the degree of q of x, then we do this long division thing, and there's like a polynomial part. And the polynomial part, whatever it is, whether it's a quartic or a linear term or whatever, that's going to completely dominate the story for large values of x. So we're going to focus the rest of our attention on the case that's not the case. We're going to focus our attention that here we have, this is something like, has the degree of p of x is less than or equal to the degree of q of x. This is the part I actually test much more vigorously in this course, okay? So we'll spend the rest of our time talking about how to graph that. In this case, the asymptotes for the graph are much simpler. There are two cases. So I'm missing an if here. Theorem. If, then, case number 1. And this is usually the case. If the degree of p of x is strictly less than the degree of q of x, then y equals to 0 is the horizontal asymptote. And what that means is that the graph eventually gets sucked into, we're gonna abbreviate that as HA, because writing out horizontal asymptote multiple times gives none of us joy, me least among you. So if the degree, let me put that in words, if the degree of the numerator is smaller, strictly smaller than the degree of the denominator, then y equals 0 is a horizontal asymptote. Step number 2, if the degree of p of x is equal to the degree of q of x, then y equals to a sub n over b sub n is the horizontal asymptote. Where I'm assuming that like p of x is equal to an x to the n plus an minus 1 x to the n minus 1 da 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 plus a0, and q of x is equal to bn x to the n plus bn minus 1 x to the n minus 1 plus da 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 plus b0. So when I say the degree of the polynomial, what I'm talking about is the largest non-zero power which appears non-trivially in the formula. So the leading coefficient is what's called a sub n and b sub n for this case too. That's the largest, that's the coefficient of the largest power which appears in the polynomial non-trivially. And you can see here what happens, right? Let's look at it for a second. If we've got y is equal to p of x over q of x, how's that go? Well, we've got an x to the n plus an minus 1 x to the n minus 1 plus da 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 plus a0 divided by bn x to the n plus bn minus 1 x to the n minus 1 plus da 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 plus b0. So that's the formula for my function. I want to talk to you guys about what happens to that formula for x really, really, really big in either direction, positive or minus, plus or minus infinity. So what I can do is I can take this expression and I can divide the top and the bottom by x to the n. If I do that, what happens? I get an plus an minus 1 divided by x plus da 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 plus eventually a0 divided by x to the n divided by bn plus bn minus 1 divided by x plus da 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 plus b0 divided by x to the n. So I divided the top and the bottom of the formula by x to the n. Then what? Can you guys tell me what happens to this formula as x goes to plus or minus infinity? If you look at it, this just goes to what? What happens when x is really big? You've got division by something really big, either in the positive or negative sense. What happens to those? Like what's 1 over a million? What's 1 over a billion? 1 over a million to the 10th power or something, right? It's what? It's very small. So while all that remains in this expression is what? These first two terms, right? So we just get an over bn. So that's why this theorem's true, is this calculation. So let's put it into practice. Let's look at some examples. Example 3. Suppose we've got y is equal to x over x squared minus 9. All right, can we graph this? Let's see how it goes. And then, so let's do that. So first order of business is to, factor. Second order of business, and it really, there's no, I say first order, second order, but honestly, well, no one cares about the first order, but if you're looking at this, what's the horizontal asymptote? No, those would be vertical asymptotes, because that's where you'd have x equals to 0, y equals to 0. Why is that? Yeah, because the numerator has degree 1 and the denominator has degree 2. So eventually the denominator wins and forces it to go to 0. So that's why we get sucked into y equal to 0 eventually. Now the vertical asymptotes are x equals to plus or minus 3, because I have division by 0 there. Now, to complete the story here, good practice to draw the sign chart. So the sign chart has the critical numbers, which in this case are minus 3, 0, and 3. All right. Okay, so the horizontal asymptote's kind of boring here. It's just the x-axis itself. Y equals to 0 is the horizontal asymptote. The vertical asymptote, I will try to stick with this color code the rest of my lecture. I will make my vertical asymptotes red. So here we go. There we go. X equals to minus 3. X equals to 3. These are my vertical asymptotes, right? What else do I have? Well, I need to, oh, I know what I need to do. What good is a sign chart if we don't put pluses and minuses in it? So how do you start here? Plug in the number. How about plug in like 4? If we plug in 4, we got what? Positive, positive, positive. 3 pluses, also known as positive. So we got pluses here. And then we got minuses here. And then plus. And why am I flipping the signs? Because we don't have a multiplicity which is even on any of the factors. The multiplicity on every factor here is odd. So we flip signs by the sign flip theorem. Now I can graph. So let's do that. I'm negative to the left of this, so it's got to do something like this. All right? The graph has to blow up at the vertical asymptotes. It's either got to go to minus infinity or plus infinity on both sides. Now it can go infinity on one side, minus infinity on the other, infinity on both, minus infinity on both. It kind of depends on the sign chart. Here it's going to go down to minus infinity on that side. It's going to go up to infinity on the other side. See that? Like that. Now what else happens? Oh, look at that. It's got an x-intercept of 0. I should probably put that in there. That is where the numerator is 0, right? And so my graph has to go through there. And then what happens? Well, it has to get really large and negative down here. So it's got to look something like this. Now, the other section was like, well, how do you know it curves right there? I don't. This is a sketch. All right? Like you could make it curve a little bit different. To figure out exactly where the curve, where the hump in the graph is, you need calculus. But can I teach you guys calculus? No. Oh, dang it. I would have done it for free. Let's see here. So over here we have this. You're like, one math course at a time, please. All right, fine. Oh, well, thank you. So, care to elaborate?
Why is this one down in the negative, like that one? Why is it down in the negative? And then why is it then curve? And then why is it go positive?
Because the sign chart, so there's some, here's the rules of the game. I have to be getting very large in either the positive or negative direction wherever I have division by 0, which is where I have the 3 and the minus 3. So I have to either go up or down at the vertical asymptotes. Stuck with that. The other thing I'm stuck with is I have to get drawn into the x-axis eventually, long term. The other thing I have to take stock of is I have to go through x-intercepts if I've got any. I do. There's one here. And last but not least, this all has to be consistent with my sign chart for the function.
Wouldn't the 0, 0 be a whole?
Not here. There's just 0. I can plug in 0. I get 0 over minus 9, which is 0. I do have a horizontal asymptote of 0. You can cross the good question, you can cross a horizontal asymptote. Oh yes. Horizontal asymptote and vertical asymptote, very different. In fact, you can, and I did right there. I see mind has been blown. Yes?
I don't know if it's been blown. I think it's just really confused. I feel like everything I've learned is a lie.
Well, not everything.
Most of it.
I hope it wasn't things I taught. See, I mean, I would like to think about how to create a consistent, like, false college algebra series of lecture, just again encapsulating all of the wrong ideas, but in somehow like self-referentially enforcing wrongness, and then to get students to be worse, like a meth prank channel, It's a dream I have.
Yeah.
But I only have a few examples for this,
Do that to your class that only has one student.
At the moment, it's mostly just stuff like this, like 7 over 17 is really just really just equal to 1, because of course you can cancel the 7s, right? Because then it's 1 over 1, which is just 1. So most of my math pranks are like this at the moment. I got to do better. It's not enough. I can do better. I also can do things like this. I'm thinking there's going to be a lot of this. A lot of that. I like that one a lot. Because of course the square root of x squared plus y squared is like the square root of x squared plus the square root of y squared, which of course is x plus y, right?
Yeah.
It's wrong on many levels what I just wrote. Well, the first thing is that the square root of a sum is not the sum of the square roots. And the second thing is that these should be absolute values. Because the square root of x squared is the absolute value of x and the absolute value of y.
I think I need to withdraw from this course.
Well, don't do that. All right, so let me get back on track here. Let me try to confuse you guys in a more orderly fashion. So to recap, the steps are factor it, identify your asymptotes, identify your critical points, draw the sign chart, put it all together, graph. That's it. Let's do another one. Example 4. What if we had y equals to something like 3 times x squared minus 4 over, excuse me, I don't know, x squared minus 1. That one's relative. This should be nice, and it's pretty symmetrical, this one. So if we factor this, what do we got? So how about this one? What do you guys think? What's the y asymptote going to be here? The horizontal asymptote, rather, for this one. Which case am I in? Am I in case 1 or case 2? What's that? Case 2, right? Because my degree in the top and the degree on the bottom, they're matching, they're equal. And so what's the leading coefficient upstairs? 3, right? So I get y is equal to 3 over 1, which is also known as 3, is my horizontal asymptote. Yay. What are my critical numbers? Well, right. Right, exactly, yeah. So plus or minus 1, plus or minus 2, and I'll try to put them in order like that, something like that, right? The 0 is right in the middle of minus 1 and 1, so I'm going to draw that right down. So I try to draw my axis right below my number line, just to keep all things all nice and pretty like that. It just helps me to organize things a little bit. What are my vertical asymptotes going to be in this one? Right, x equals to plus or minus 1, vertical asymptotes for this one. Because I have division by 0 there. All right? Like that and like that. Now let's put the plus and minuses in my sign chart. We start out, all my examples are the same. It's always positive over here. You're like, until the test. I'm like, yeah, fair enough. I feel guilty for giving the same example over and over, so I change it on the test. You know, what can I tell you?
Don't feel guilty.
Don't feel guilty. It's too late. So let's see here. So if I plug in like 3, it gives me plus. But then these are all odd multiplicity, so we flip signs each time. Don't worry, I'll do one without the flipping soon. Maybe next one. All right, so where are my x-intercepts? Do I have any? I do. I've got an x-intercept where? -2 and also 2, because that makes the numerator 0, which gives us an x-intercept. But the other thing I haven't yet pictured, and I'm sadly going to have to choose a different scale for the y-axis given my stupid choice of, like I'm sorry guys, I'm going to have to use a different scale on the y-axis. I'm going to put my y = 3 like here, just for the sake of fitting it, okay? Sorry about that. I would like to make it the same, you know, the same scale, but I just can't with this space I have here. So eventually, the graph is supposed to get sucked into the y = 3. So what's the graph have to look like? Well, let's start out here. We're positive to the left of -2, which means we've got to do some kind of thing like this, all right? So we're like approaching that asymptote, but we can't cross it there. And then we go negative here, like that. On the other side, we've got positive here, and then we go negative there, like that. Now, what's the story in the middle? There is in fact a story in the middle. What is it? It's positive, right? The sign chart tells me it's positive. So what it has to look like in the middle is something probably sort of like this. And if I had to guess, I probably can tell you that the turning point's actually on the y-axis. Because of the symmetry of the problem, it's probably right there. And I could add a y-intercept if you wanted me to. Just plug in 0, see what you get. You know, I get -12. I get -12 over -1. So this happens at 12. So my picture isn't quite right. That's 12. This is 3, right? This is very much a sketch, right? It's not a very accurate picture, but it does have the gross shape of the graph correct, all right? So when I say sketch the graph, this is what I'm after, is like the general shape of it. And we can try to improve on it by adding points if we want to be more, you know, accurate to scale. Any questions? Let me do some more, if I can. All right, example 5. Suppose we're up against f of x equal to, let's see here, how about x squared plus 3x plus 2 over, oh, I don't know, x cubed minus, or rather, plus x. There we go. This one's a little bit different than what we've been up against so far. I'm still not entirely happy with it. I'm going to throw in, for good measure, a x minus 8 squared. There we go. So let's see if we can figure this out. So first order of business is to factor everything. So first of all, before I do anything else, the horizontal asymptote is clearly 0 because the denominator has degree 5, whereas the numerator has degree 2. This is definitely y = 0 is the horizontal asymptote, fine. Now we can factor, and we've got x plus 1 times x plus 2 upstairs. Downstairs, we've got x times x plus 1 times x minus 8 squared. Aha. So we have y equals to f reduced of x if we have what? We can cancel. You see what it cancels here? See this right here? We can cancel that out as long as x is not equal to minus 1. And that leaves us with what? Well, it leaves us with x plus 2 over x times x minus 8 squared. So this is for x not equal to minus 1. So you can basically graph y equals f of x by graphing the reduced function and then simply punching a hole in the graph where x is equal to minus 1. Then that's what we're going to do. So how do we graph the reduced function? Well, we just need to create our sign chart for the reduced function, right? I've got what? I've got minus 2, I've got 0, and then I've got, I guess, 8 over here, right? Those are my critical numbers. And because I lack imagination, we have plus to the right again, because if we plug in a big number, we get positive over here. Again, don't assume that's always the case. I may make it so it's not the case on the test. Think through it. Then how about this? Oh, look, multiplicity 2. The story changes this time. We don't flip. We stay plus over here as well. And then 0, we flip because we've got an x. And then minus 2, we flip because we've got an x plus 2, multiplicity 1. All right, let's put it all together. Put it all together, what we got? We have got ourselves a vertical asymptote at 8. There's also the vertical asymptote at 0. Doesn't have to be there, right? It could be at a constant if we have matching degrees. Now what else? I've got a x-intercept at minus 2. See that? And yeah?
No. How come 0 is horizontal, not vertical?
Oh, I've missed a vertical asymptote though. Where else do I have a vertical asymptote? What's that? Oh, you're asking me why don't I have a vertical asymptote here? The answer is because I was getting to it. X equals to 0 is so this one's kind of funny. X equals to 0 is a vertical asymptote. Because why? Because of this x right here. The x in the denominator of the reduced function.
Why do we have the green?
The green asymptote, again, that's because we have degree 2 over degree 5, so the numerator has smaller degree than the denominator. Y equal to 0 is the horizontal asymptote. It's the long-term behavior of the graph. Now, all right, so here it is. So we've got, it's going down, down, down to minus infinity here. It's going to plus infinity over here. And then it must be bending back up and like that, right? Now where exactly it bends back, I'm not saying, like, I don't know. It could look more like this, guys. I really don't know without doing calculus to figure out where the turning point is, okay? But you guys said I wasn't allowed to do that, so I won't do it. Now here, it passes up, it gets positive, but what has to happen is it has to turn back to go like that long term because it has that y asymptote, the horizontal asymptote of the x-axis. And over here, it's a volcano at 8, so it looks like this. All right, and then that just smoothly goes like that. How come it goes to negative infinity? Well, the difference is that I have plus to minus. So I have a negative minus infinity from that side, and I've got a plus infinity from that side. See the difference in the sign chart? Whereas at 8 rather, I have plus on both sides, so it's going up on both sides. I've got a volcano. And that's kind of generically speaking what you should look for in your graph. When you have, when you have in the denominator a factor with even multiplicity, you'll get a volcano either opening up or down. I guess if it opens down, it's a bottomless pit. But, either have a volcano or an endless pit of despair. But on the other hand, if you have plus and minus corresponding to vertical asymptote, then you can expect one of these ones that rips up to infinity on one side and minus infinity on the other, like this. So the only places we can change from positive to negative in the graph are either x-intercepts, vertical asymptotes, or also it could happen at a hole in the graph. Let's look at that. So example 6. Oh, I didn't finish that one. Where's the hole in the graph? I forgot to do my hole in the graph. My bad. Where's the hole? Hole in graph where? At -1. So it's at -1 comma the reduced function of -1. So what's that equal to here? I plug in -1 into my reduced function, I get -1 plus 2 divided by -1 times -1 minus 8 squared, which apparently is equal to -1, I guess that's a 1 over 81? Did I lose a minus? I think it's a -1 over 81. So that's like here. Obviously this graph's not very much to scale, but this hole in the graph right there would be -1. Well, I guess I had it almost right, if I did that right. What that means is if you actually plug this into Desmos, it's much less exciting. Like it's very close to the x-axis, and then it just spikes. It's really hard to see if you actually were to graph it with a graphing calculator or something. But there's the hole in the graph. So to find the hole in the graph, identify the thing that's been canceled out and plug the whole x-coordinate into the reduced function to find out where it is. Another one I should give you guys today is something like this. Y equals to x minus 1 squared over, x squared minus 1. So the way this works is I've got x minus 1 squared over x plus 1 times x minus 1. So you see what happens here. We get x minus 1 over x plus 1 for x what? X not equal to 1. And so the graph, what's the y asymptote here? I mean the horizontal asymptote. Degree top and the degree bottom, they're both what? Degree 2, right? So this we're looking at ratio of the leading coefficients, 1 over 1. The horizontal asymptote's at 1. Oh man, I forgot to draw my sign chart. My bad. Well, I'm going to have to violate my usual pattern and draw it down here. So I've got -1 here, 1 there, and well, surprise, surprise. I've got pluses here, minuses there, pluses over here again. I have a vertical asymptote at x equals minus 1, like that. And, okay. And I have an x-intercept where? Well, got to be careful here. You'd like to say at 1, but can I say that there's an x-intercept at 1? I really can't, see, because the x-intercept is actually a hole in the graph. X equals to 1 is not defined for this function, for this graph. I have division by 0 there. It's outside the domain of the rational function. So I have a hole in the graph. But it does look something kind of, sort of like this. Like that. And then like this. Where is this hole? It's at 1, 0 in this one. So if this is you know, if this is y equals f of x, can you guys tell me, you know, what's the range? What's the domain for my function? I heard the domain of f of x was equal to minus infinity to what? Negative 1, okay. Union what? Negative 1 to 1, union 1 to infinity. So I have to delete both 1 and minus 1 from the domain. They're both troublemakers. How about the range? Yeah, I'll write it this way. Y in the real numbers such that y is not equal to what? You never get 0, and you never get 1. So both the domain and range are both missing 2 points from the whole reals. All right, so the next thing we'll do is try to like reverse engineer. So like imagine that I gave you a picture of the graph and I asked you to come up with a formula. Could you guys do that? How about this one? So suppose you want your graph to look something kind of, sort of like this. It's got a volcano here. Whee! It crosses, it's got a hole in the graph right there, and then it just does like this. And let's put the hole at minus 1, 2. And let's put the vertical asymptote at minus 2. Can you guys tell me what a formula would be that would do this? Example 7. So this is kind of backwards of the examples we've done so far today. Here's what you do. You'd write y equals to something like 1 over x plus 2 squared. See, that would give me everything. That would give me everything I want, except for what? Except for the hole. How do you punch a hole in a graph? It's very simple. What you do is you just multiply the graph by x plus 1 over x plus 1. This silly fraction is 1 everywhere except for where it's undefined, namely minus 1. That punches a hole in the graph. Now, how do I force the hole in the graph to be where I want it to be? Well, that's where I realize, wait a minute, I can rescale this graph by any multiple. See, I can put an a out front. And it's still the same shape. And see, then I just have to say, you know, a over, you know, minus 1 plus 2 squared should be equal to what? It should be equal to 2. I solve that. That tells me what a to put in there to make it fit that hole. And that's how you do it. This is how we could reverse engineer one of these examples. But anyway, hey, listen, Wednesday we'll do more. We have a quiz and stuff. But remember, Friday at start of class, mission 2 is collected, so you need to be done with it before then. And we're talking about the solution to mission 2 in class Friday. So Wednesday, you can ask me questions about the mission. We can talk the whole class about the mission. This is the material pretty much for it, for test 2. So